demonstration of the trapezoid rule. Um, so I'm opening up the notebook, Trapezoid Rule New, from the course webpage, and I'll just start at the top. Um, Exit will restart the kernel, so it's a little quicker than going to the evaluation menu and picking quit kernel and then start kernel, or restarting Mathematica altogether. And it's a nice way to clear your workspace. So let's recall that the formula for the trapezoid rule, and this is really, of course, the trapezoid rule for a function f over an interval a to b with n subdivisions. And the endpoints of the subdivisions are these x0 through xn. That you take the sum of the function values at the xi with the starting one and the ending one weighted half as much as all the ones in the middle. And then you multiply that by b minus a over 2n. So 1/2 times the size of the interval. Now you can write that almost exactly like it looks in Mathematica. And this is actually code. This isn't just typesetting. So if I hit Shift Enter, it evaluates it, starts up the kernel, and indeed, if I want to try it out, I can use a function like x squared, which remember we can write as, in terms of a pure function, as pound sign, that's the variable squared. I can integrate that from 0 to 1. And I'm going to do it 0 to 1.0, so I'll get a numerical answer instead of a whole bunch of fractions summed up. And I can do it with 20 intervals. And you see that as I add intervals, it gets closer and closer to the true value, which we know to be a third, right? So how did we type this in? Well, we used the palettes. So I've got the palette over here. This is the Basic Math Assistant palette. I get it, I'll just close it and open again, by going to Palettes, Basic Math Assistant. And then if we pull it over here, you see that it has things in the bottom row like indefinite integral, definite integral, sum, and product. Now I can definitely use these things as just typesetting things like equation editor in Word. For instance, if I have the sum from 1 plus 2 plus 3 all the way up to n equals n times n plus 1 over 2. That's a formula you should maybe remember from 2250. Then I can write this by clicking on the sum box, and then I can use tab or click to get around to these boxes, and I can actually write out I equals 1 to n I, and then I can put in an equal sign here, and it looks nicer. Again, just like equation editor in Word. Now here, I'm in a code box. So in a code box, I can do the same thing. I'm going to pick the sum item. I'm going to type I equals 1 to n I. Again, I was tabbing to get between the boxes. And I shift enter, and you see that Mathematica will actually evaluate the sum. Now, of course, for the sum of I, you know this, but it's a handy trick if you, for instance, want to do the sum of 4i squared. I got the exponent with control 6. Now I can use control space to get back down to the main line, plus 3i plus 7. And it's just as happy to do that, which is actually a significant savings of algebra. Okay, so let's take a look at a first example with the trapezoid rule. So if we take the integral from 0 to pi over 2 of sine x, well, we know that the integral of sine is minus cosine. So we evaluate minus cosine at pi over 2 minus minus cosine at 0 and get 1. And in fact, we can write this using the integrate function, and we can also go over here and click on the definite integral and type integral from 0 to 1 of sine x tab dx. Of course, it would help if I put in the right integral. 0 to pi over 2 sine of x dx, and I get 1. Okay, now if I want to compute an approximation using the trapezoid rule, I'll just use our trap code. I'll evaluate pi over 2 to 16 digits. It would be equally good to take pi over 2.0. That'll convert it to a machine number with 100 intervals. And you see that we get point quad 979, which is pretty close to 1. Now we can compute the number of correct digits, and we'll do this by taking our usual correct digits code. So it is the approximate value minus the true value divided by the true value, relative error, absolute value, log 10, and then absolute value, because of course this is the actual relative error, and if we have 8 correct digits, the relative error will be 10 to the minus 8, so the log 10 result will be minus 8. We're going to take the absolute value to make it a count of digits, and then multiply by 1.0 to get a numerical answer. So for instance, we see we're supposed to have 4.68 correct digits in this trap 100. And here are the 4 digits, and then the 7 is pretty close to the 9. So it's 4.6 correct digits instead of just 4 correct digits. Okay, now we're going to talk about the error formula in a few minutes, but you remember that we derived the error formula and it was proportional to h squared. So if we take the error data, and 1 is the true value, trap is the approximate value, we can get a table of errors for anything up to 10 to the 12th points. Now, it's kind of amazing that I just did a sum over 10 to the 12th points in that amount of time, but modern computers are indeed really fast. You'll see the problem is that after you get to 10 to the 8th, it gets indeterminate. That's because it can't compute the error in machine numbers. So at 10 to the 8th, the number of correct digits is pretty close to the maximum number of 16. So it's indeterminate after that. So I'm just going to reduce the upper limit here to 8. So our error data exact only involves particular numbers of digits. So now I'm going to go ahead and fit a linear model to that. And I'll make that error data exact. And you see that when I fit the linear model to that, I get the linear model 0.875 plus 1.93614x. So that is indeed very close to 2, which makes us happy. So here we go. We're going to plot the number of correct digits versus the number of intervals in computing the integral from 0 to 2 pi of sine x dx with the trapezoid rule. So I've plotted a horizontal line at 16 here. You can see that the actual data, that's these dots, um, is pretty close to the linear fit, which is this line, the linear model, um, and that it tops out right around 16. Here the number of intervals is 10, 1,000, 100,000, um, uh, and so forth. Okay, so what's with this thing, right? Well, I'll click on it. Um, so if you click on it, you see that it's a sequence of length 5 with a byte count, whatever that means. And you get this interesting box which says uniconized. So I'm going to click it. So what you see is this is a bunch of kind of ugly plotting options. Um, so you can click on it if you want to see the innards. If you don't want to see the innards, you can select it, go to Edit, and pick this for iconize selection, and that will just hide all this stuff. It still executes, but it doesn't show. Okay, so notice that we're actually getting quite good accuracy. We're getting quite close to 16 digits. Um, this is because, unlike numerical differentiation, where the number of correct digits never got all the way to 16 and topped out fairly quickly, numerical integration is numerically stable. So basically all we're doing is summing things. We have no reason to believe that these things are things of opposite sign that almost cancel out, and they're probably not. These are all values of sign between 0 and pi over 2, so we're summing a bunch of positive numbers. Of course, eventually, if you sum a very large number of positive numbers, you can get round off error from the sum. But even at 10 to the 8th things in the sum, 100 million, it's still not a problem, as you can see uh, from the digits here. They're just climbing happily. The other thing you notice is that really this is much slower than you think it should be. So to get full precision, we really did have to go to 10 to the 8th. 100 million grid points, which probably means several hundred million arithmetic operations, because of course you have to multiply by 2 and so on and so forth. Okay, so, and you have to compute the location of the grid points. So if you see what's actually in the sum, right, I have to recompute b minus a over n every time, multiply it by I, add a, evaluate sign of it, multiply it by 2, and add to the sum. So that's quite a bit of arithmetic. Okay, so let's think about the theoretical error bound now. We saw, but we're going to do that in the next version, next segment of the video.